All right, good morning, good afternoon. So today I got a special presentation for you today, which is a previous work that was completed in, I believe it was 2019. This is related to a cognitive hybrid particle swarm optimization simulated annealing work to solve a combinatorial optimization problem. So this is work that me and my supervisor completed together. Ultimately, one of the things that we wanted to do was improve modeling of cognitive processes using these two techniques, the particle swarm optimization and simulated annealing, which I'll get to in the methodology. One of the things we want to do was solve some simple combinatorial optimization problems, one of which being the more famous NP-hard problem, the traveling salesman problem. So quickly, just the hybrid particle swarm optimization, simulated annealing, they combine to solve a nonlinear optimization. Ultimately, it's nonlinear optimization of a problem. So in particle swarm optimization, you don't necessarily converge at the same rate. And simulated annealing introduces a stochastic optimization form. It's used in many different ways: Bayesian networks, load balancing, and supercomputer systems. So these tend to be NP-hard problems where there's a combinatorial optimization. There's a certain arrangement of things you need to do, and you're trying to think what is the best arrangement or best way of doing it, and the smallest amount of units of time or instruction sets. So ultimately, that's what this problem comes down to. And because something like the traveling salesman problem is so difficult, one of the things we want to do is how well can a combinatorial optimization architecture, such as hybrid particle swarm or simulated annealing, can be used to solve these problems. So there's a lot here with regards to relevant literature, which I'm not going to go into. I'm going to get right into how standard particle swarm optimization works. Ultimately, the things that we want to be concerned with is this position vector, and this can just be a position vector in d-dimensional space. And then there's this vector set. And you can just consider this as x being sort of the position in this d-dimensional space, exactly where it's located, and v being velocity, which is to say sort of a positioning. So this velocity can be many things. It can sort of be a position vector, or it can be, we'll actually get into it a little bit later on in some examples on the right here. So the position vector can just be, let's just say it's an arrangement of 4 numbers here, 11, 21, 8, and 4. And let's just say the combinatorial optimization problem we're trying to find is we're trying to, the best, there's some sort of loss or global function, and we want the final arrangement to be 8, 4, 11, 21, but we don't know if that's the case. So the question is, how can we perturb this space here such that we get 8, 4, 11, 21? Well, one thing we can do, because it's a position, like the final solution we're trying to find is a position, like we want 8 first, 4 second, is that our velocity vector in this case is going to be a set of positions. So in this case, the velocity vector is telling us, hey, take position 1 and switch it with 3, and take position 2 and switch it with 4. So that's sort of what you see here. 1 is switched with 3, and 2 is switched with 4. So because this velocity vector is applied on this position vector, we actually get x at t plus 1, which is sort of the next time step. We get the arrangement that we want, right? So ultimately, the question just is, how can we prearrange a position vector, velocity vector for our application to find this final position vector that we want, which is some sort of global solution. So if we characterize this x as this x and this v as this v in this d-dimensional space, one of the things that we also do in particle swarm optimization, the whole idea behind particle swarm is that, let's just say we have these swarm members. So these are like different agents. And let's just say in this case, what we want to do is find this spot. So x marks the spot. So we want to find this x. Okay. So the question is, without knowing where this x is, all these little points can do is they can look in their immediate vicinity and try to find where this x is. So this little circle is going to go this way. This one might go that way. This might want to go that way. And this might want to go that way, right? So as some of these units, or some of these swarm agents get closer to this x, what we want is that this x, as it gets closer to this, it can actually communicate. It sends a certain amount of information to its neighbors saying, hey, by the way, I actually found the x marks the spot. Please join me. right? So in this case, it's going to communicate that information, and then all of these swarms are going to approach this X, right? So it's a balance here where each swarm position thinks it's found what it thinks is the X, but let's just say the big X is here, but there's a lot of smaller X's here, right? So the thing is, these units don't know that the smaller X is here, and this unit knows that the bigger X is there. So it's going to have but it doesn't know in the end if it's a big X or a small X. So what you kind of want to do is these particles are slowly going to communicate what it thinks is what it's found as its biggest X, and the other ones are going to tell it where its biggest X is, and it's going to have a balance between how much it pays attention to its own performance and those of its neighbors or swarm. So particle swarm optimization is ultimately this problem carried out. So that's hybrid swarm optimization, and this is sort of summarized in this equation here, where this velocity, its position that it's going, is influenced by three things. One of the things is it's influenced by its own, how much this W, which is how much it pays attention to its own behavior. So it's kind of the selfish coefficient, and it's saying to itself, I want to pay a lot of attention to myself, so this W is going to be close to 1, right? And then the V is going to be its velocity. So it's going to say, I'm going to go where I want to go because I'm selfish. As opposed to these two other coefficients here, which it's personal best and global best. So this right here is where it is at this moment of time. So it says, I'm getting really close to the X. I want to pay close attention to it, so I'm going to stick here. And this coefficient here, after this positive here, is saying, it says, you know what? I care a lot about where I am now, but at the same time, I've seen a bigger X somewhere else. So I'm going to balance both those things. The fact that I want to explore for a bigger X, at the same time, I want to exploit the fact that I might have found a good X here, so I'm going to dig a little deeper. And then, of course, the whole point of particle swarm optimization is that we have the second term, G best, which stands for global best, which is to say, I'm also going to pay attention to all my other friends on the playground that I found the X marks the spot for the treasure. And I'm going to add that in, I'm going to influence that too. So given these three influences, we're going to call it, the important things to consider are these W values: weight, C, C. So weight being how much it pays attention to itself, C1, how much it pays attention to its best, what it's seen previously, and C2, how much it should pay attention to everybody else. Ultimately, it's a balance, right? If this WT is driven to 1 and the other ones are driven to 0, it's as selfish as it can be. C2 is an example of if this is driven to 1, the other ones are driven to 0, then C2 is going to say, you know what, I'm pretty much blind. I can't really see where X marks the spot. I'm just going to pay attention to what everybody tells me is the best place to go. So it's a constant balance, and as you carry out these combinatorial optimization problems, you want to sort of adjust the impact of these things as you sort of go throughout solution space and look for solutions. I'm not going to get too much into standard significant simulated annealing just because it's kind of a little bit trivial and not that important. All the things is what this pretty much does is simulating adds a stochastic nature to it. So everything that you sort of see here, whether it be these weights, these C1s, these are coefficients. R1 and R2 are a random number, so there's some randomness added to it. And that's just because we don't want it to be deterministic where it's constantly doing the exact same thing. We want it to, after certain iterations, sort of push itself in another way. So if you're someone on the playground, you're looking for X marks the spot, it's as if a parent came by and then pushed the kid a little bit, one way or another, and then they went to another sandbox and we're looking in that one. So that randomness kind of helps when it comes to finding X marks the spot. But additionally, the simulated annealing actually says, once you get to X marks the spot, right, and you know you found a better one, there's going to be a little bit of influence that sort of says, you know what, you found a better X marks the spot, but just for the time being, pretend like you didn't, okay? And that's just because everybody thinks they found the big X marks the spot, when in reality, it's just a small one. So it prevents the influence of these small X's from getting closer and closer to the X, and actually gives them a random chance of, while they're being influenced in one way or another, of randomly moving somewhere else, right? So it kind of is contrary to what you think, which is to say, when you find better solutions, you're getting close to X spot, you want to get closer and closer to it because you want to explore it a little more. But with this little bit of a push, elsewhere, what you find is that it works out better than, on average, better than not. So a lot of things to be considered here. Pretty much the deterministic nature of particle swarm and the randomness that we get from simulated annealing, which is represented in this expression, which I'm not going to get into. Now that we kind of understand this, we get this idea of these coefficients. So I was telling you about C1. I'll highlight that because that's a little easier to see. With regards to these C1 and C2, so these are these coefficients, again, between 0 and 1. How much should I pay attention? How much shouldn't I? And this coefficient dampening, this is important. As I was kind of saying, it's a constant balance between the three. The personal, at the moment, the personal I've ever seen historically, and the best that everybody else has seen. This dampening, what it does is it slowly decreases. So when we start out at the first iteration, remember we have a bunch of kids on the playground and they're all looking for X marks a spot. We want them to spend a lot of time looking themselves. So that's why we drive the inertial coefficient. So it's like the personal preference, very high. And then we don't care too much about what, this inertial sort of goes like how much it should push. It's like the big step that it takes. So it takes big steps takes big steps. But as time goes on, the swarm coefficient, which is the best out of everybody, is very low. But at the same time, we want to increase that influence over time. As these kids on the playground, again, these agents, go throughout the playground, they're slowly going to find better solutions. And as they go on in time, we want everybody else to pay more attention to it. So that's where this increases. Personal and inertial, it's kind of confusing because of the terminology, but this is inertial, this is personal. It's personal best, inertial as in it's inertia, the big steps that it's taking at this moment of time. So this just goes to show that the inertial, which is how much it's paying attention to what it's doing right now, decreases over time, and the personal increases over time. And ultimately, we have all these agents jumping all throughout the problem. And then finally, we want them to sort of say, okay, we're done. We've exhausted. What's the best solution that we found? Who has the biggest X, right? So with these dampening coefficients, we're paying attention to different influences. And this temperature ramping, what this kind of does is with the X marks a spot, I was saying that the simulated annealing causes it to, instead of going to the smallest X, it might think it randomly jumps elsewhere. We also want to influence that effect, which is to say at the very beginning, we don't want it to randomly go anywhere. And that's just because it's already doing that through these influences. But as it gets closer to the end, rather than it getting super close to these X's and paying too much attention, we want it to randomly jump elsewhere. Okay. And that helps in sort of adding a little shock to the system. And again, ultimately, we want all these particles to get to what it thinks is the biggest X. So the question is, how do we influence that? So here's sort of the quick pseudocode for that. There's a lot of initialization and running through iterations, and it's looking, okay, is the global best better than the personal best? If so, then your personal best becomes the global best. This is just the code that sort of says, hey, if you found what the best solution, well, it becomes the best solution for everybody else, and then use that to influence the positions. So that's what we see with these expressions here. The question is application. So how do we actually test this? So as I was showing here with these X marks of spots, we're actually doing the exact same thing, but we're applying it to a traveling salesman problem, where the traveling salesman problem just says we have an assortment of dots here, and we have to visit every location at least once and then return where we went to where we got to. So the length of these arrows is distance, and ideally we want to minimize this distance. So that's the solution to this problem, is minimizing this distance. A poor solution would look like this. We'd ask it to jump here, we'd ask it to jump there, and then maybe we'd ask it to jump there, right? So there's a lot of movement involved in here, as opposed to, you can sort of see the travel salesman problem is the same problem you'd have if you traveled from where you live to a nearby state or province, which is to say the best place to get there is the shortest path. And if there's a certain number of cities you have to visit, because you have to fill up your fuel, ideally you'd want to jump to the next closest one, the next closest one, and then that one. And then you have to return back at home at the end of the day, and you want to minimize. So this is a minimization problem. Okay. So with that, one of the things that we can test is we can actually look at countries such as Rwanda, Canada, and Japan, where there's a varying number of cities from 1600 to 9800. all obtained from this database. And then rather than it just being 4 points, we actually have something like Japan where it has 9,847 points. And then we slowly visit each city throughout Japan and then return where we went. It's very trivial when you look at 4 points, but when you have something that approaches even a couple thousand, even a couple hundred, this problem becomes prohibitively expensive. And that's what makes it an NP hard problem, something that cannot be solved in linear time or polynomial time. One of the things that we did was we tested 4 different models, one of which being the hybrid form using particle swarm optimization and simulating annealing at the same time, simulating annealing itself, and then particle swarm optimization itself. Ultimately, one of the things we found with particle swarm is that, okay, what do we have here? We have iterations. So as it continually goes on, it's looking for X marks the spot. How well does it do? And distance in the traveling salesman problem is the optimization. So you're trying to find the minimum of the distance. We are trying to find and minimize this distance, which is here. So minimization problem, you want to get as low as possible. What do we find when you have particle swarm by itself sort of reaches the steady state? What is this telling us? This is telling us as the model goes, the particle swarms are moving around, they're finding the best place, and then slowly the global influence overtakes the local influence, and then all the particles are saying, I found the best, everybody come and join me, and then they focus on this X marks the spot, and it turns out not to be a very good X, right? Now, when you have something like with simulated annealing, with that push that it gets, one of the things you find is that it has a much lower distance right away, and even simulating annealing alone, on average, found better local minima. So even that jump itself, that push, helped over using the hybrid approach. So one thing that I found was, I think with regards to, let's see, unique solutions 8, is that even though on average this distance was lower, what happened was, so there's some things that make sense, which is execution time. When you have more computation, more things and stateful events, one of the things that the execution time and the memory requirements go up. So you would expect that as the model becomes more complicated, you would have, well, kind of the execution time is a matter of how many steps is involved. So there's a lot of steps when it comes to particle swarm optimization because it's paying attention to all those things and making the computation. So you would expect it to be more. Simulating annealing would be 12, and then particle swarm was 1. So actually, sorry, the particle swarm optimization wasn't much, but the execution time, oh, that's how much execution time. Okay, unique solutions is how well it performs. So it found a lot of so average is just the average of the distances. Unique solutions, so this is how well it performs. So particle swarm by itself performed very well for unique solutions. And if execution time, I think I normalized that to 1. Yeah, normalized to particle swarm at that. Oh yeah, and everything else is a factor on that. So simulated annealing actually, sorry, takes the most time. Hybrids take the most time. And then the lowest would have been, again, normalized to this one. That's why it's 1. So this is saying it takes 3 times longer than this, 7 times longer. So the simulated annealing ones actually in the end took longer to find its solutions. And again, because of those jumps that it had to do, it was constantly trying to find better solutions. So that's why you actually tend to have a lot of noise with simulated annealing. So it tends to be very noisy as opposed to particle swarm. It's smoother. And that's because that stochastic pushes it. Yeah, I almost got to remember what the conclusions were. So for larger instances of the traveling salesman problem, the higher hybrid variant was able to find better objectives when it was stuck in local minima. Well, both were alone were stuck in minima longer. So in the end, it didn't come down to, is the hybrid one better in all cases? It was sort of so that it worked better in some cases, but not other. And ultimately, it's this balance of achieving a global objective, which in this case was minimizing the distance, right, for a traveling salesman problem. And pretty much the novelty was this coefficient ramping schedule. So very often these solutions, so why PSO kind of worked very well and found these unique solutions ultimately came down to a lot of these coefficients are selected and are static for most applications. So you choose them and then you never touch them again. But this dampening coefficient that was implemented here allowed it to change over time without interaction from a user. And then ultimately, this is what improved the performance. Yep. So overall, the coefficient ramping and the hybrid model played a part in preventing conventional particle swarm from overcoming the influences of personal and swarm. Ultimately, that dampening caused it to sort of consider the benefits of paying attention to what it thinks is the best and those of everybody else. So that was a paper from what would be 5 years ago now. It's a little hard to remember what I did, but ultimately that's what the takeaway was. This was a precursor work to the, I guess it would have been the hybrid particle swarm optimization with tribal coefficients work, which is a separate paper for that. So this was a preliminary work. This is my first publication. So this was a great help in all the further work that I did. So with that, you can leave questions and concerns in the comments and I'll be sure to get back to you. And thanks for watching.